Hello, my name is Pardis Miri. I'm a postdoc at Stanford University, advised by experts in the areas of affective science, computer science, and neuroscience. I take a multidisciplinary approach to design, build, and evaluate vibrotactile technologies aimed at facilitating affect regulation in general population and soon in the vulnerable population of children diagnosed with autism spectrum disorder. Before I begin, I'd like to define two terms that I'll be using throughout the talk. First one is affect. Think of affect as an umbrella term for emotion, mood, and stress. And the second one is affect regulation. Consider affect regulation as things that we do to cognitively or behaviorally alter affective states that we judge to be unwanted or context inappropriate. So this is a pre-recorded talk in which I will cover two of my papers accepted by CHI 2020. The PIV journal paper discusses the design and development portion of my work. For example, how we think about the design space for affect regulation technologies. How do we leverage the knowledge and science in affective science into our work? And how do we think about the placement pattern and personalization of a vibrotactile breathing pacer that we built? For now, I'll ask you to take my word that we built a vibrotactile breathing pacer to guide users through conscious slow-paced breathing. We took a data-driven approach to identify a suitable placement of these tactors on the user's body, which was abdomen, and we created a robust personalization procedure to ensure that the vibrations are easily noticeable, are dual phasic, and easy to synchronize breathing with. By dual phasic, I mean the inhalation phase and the exhalation phase feel significantly different from each other. The PIV++ paper focuses on how we evaluated this breathing pacer and shows that the pacer had a reliable impact on anxiety reduction. Furthermore, we tested whether there's individual difference that moderates the impact of the device on anxiety reduction. For example, we made inferences like this: individuals low on Big Five openness, which is a personality measure, are more likely to benefit from the device than those higher on the openness measure. And we found the cutoff value of 33. We calculated this cutoff actually using machine learning methods such as XGBoost and extracted Shapley values, which I will discuss further throughout the talk. On that note, let us begin. So the problem I'd like to engage today is a very common one, which is understanding situations in which people's affective responses are not well matched to the situations they're in. In such situations, people's affective state may actually interfere with and disturb their functioning. So to avoid these problems, people often try to regulate their unwanted affective states. However, in many situations, people may struggle to do so effectively on their own or with the help of others. So I wondered whether it would be possible to use technological tools to help them more adaptively regulate their unwanted affective states. And this is because technology can be available when and where they're needed. To think about where the technology could come in, it would be helpful to think about how affect is generated and regulated. Consider one affect regulation and one affect generation episode here. One generic approach is to simply assume that affect generation and affect regulation are sequenced in time. The technology is listening in and monitoring an affective signal, and when detected the need for regulation, for example, using this threshold over here, it initiates the affect regulation. For example, cues a person to get involved with some affect regulation strategy. Notice that there are two limitations with this approach. First, is that we might be cutting off someone's self efficacy because we're not directing their attention to their affective response. Instead, a technology that they may become dependent on and not feel very efficacious when they don't have it. Also, notice that we have to wait for some pretty big response that can be reliably detected by technology. The limitation of doing so is that by the time a pretty strong response gets detected, for example, over here, it becomes harder to work against the system to regulate. The affect is already up and running, and it would be harder to guarantee a successful regulation. The question is whether we can leverage the affect regulation theory to shift this regulation earlier. That is to listen to the earliest change in the affective system response, which is extremely hard to implement, by the way, and effectively bring the threshold line down. So imagine that you're bringing this threshold down. And the truth is, if we could have bring this threshold down, we would have. It's going to be very difficult. Another way of addressing this to manipulate the affective system to calm the system down early on. And to do the latter, the idea is to encourage a person toward early regulation. So the regulation can happen even before the unwanted affect is generated. So we never build a big technology detectable response. We sort of short circuit it. Now, how the technology is going to be involved in? Now, let's zoom in on one episode of affect regulation, which consists of these four stages. When regulating affect, an individual follows a process with four conscious or unconscious stages. The first stage is identifying and evaluating the need for affect regulation, then selecting an affect regulation strategy, and then implementing an affect regulation strategy. And while implementing the affect regulation strategy, monitoring how an affect regulation strategy is implemented. Is it going well or it's not? And if it's not, should it be changed to a different strategy or should it be stopped altogether? Notice that the problem with technology being involved in stages 1, 2, and 4 is that some sort of technological sensing needs to be involved. The technology may have to sense everything going around you, inside you, in your culture, in the situation to be effective. The advantage of technology being involved at stage 3 is no such a sensing is required, and it is aligned with the long-term goal of enhancing self-awareness, self-efficacy, and the belief that emotions are good and controllable. Just like how emotions don't happen to us, we don't think that emotion regulation should happen to us either. And so my central question is how technology can guide the user through an implementation of a strategy. We think that there are two ways, either explicitly or implicitly. Explicit involvement leads the user through a process that requires the user's conscious cognitive or physical efforts, for example, pace breathing or pace walking. Notice that it is upon the user to take some action while the technology is guiding them and apply some level of self-monitoring during the implementation of the strategy. Implicit involvement, on the other hand, is when the technology evokes an unconscious or automatic process that happens without insight and runs to completion without self monitoring. The user is involved in the implementation but is not deliberately taking any actions. For example, experiencing a heartbeat like vibration on the skin. There are two influential papers in this area, Doppel and Emotion Check, that I will get back to later. Between the two approaches, I was keen on explicit involvement, in particular, slow-paced breathing to manipulate the affective system to calm the system down before unwanted affect is generated. This slide is meant to summarize hundreds of studies that have shown slow-paced breathing as an effective affect regulation strategy, and in particular, those have influenced our work. For example, in Ina Kazan's book, she explains how to find a suitable breathing pace that maximizes heart rate variability for each individual. It is called resonant frequency breathing. This work informed our personalization procedure of our pacer. By personalization, I mean tuning the parameters of the pacer for each individual. Also, her observations on how functional and dysfunctional breathing patterns look like provided insights on how we should evaluate our breathing pacer. Functional breathing is effortless, slow, deep, and regular, and involves using the diaphragm. Dysfunctional breathing, like here, involve breath holding, an inconsistent breathing pattern, and a breathing rate faster than 13 breaths per minute at a resting state. It is important that when stressor is involved, the pacer doesn't elicit dysfunctional breathing pattern. And that's how we try to evaluate our pacer design in PF++ paper. Well, how do we build a breathing pacer? The first point is inconspicuousness. Notice that affect regulation often happens in social setting, and so it is important for the technology to communicate with the user in an inconspicuous way. That is why we chose vibratactile technology, and it is important for the pacer to be placed on an inconspicuous body location for privacy reasons. The second point is being biphasic. This is regarding the pattern of vibration. In a social setting, we may wish to disengage with a pacer to attend to our surrounding, like a conversation, and then we engage with the pacer again. So it is important to be able to identify which pattern to inhale and which pattern to exhale with. The third one is individual difference, sensitivity, and resonant breathing frequency. We know that as people age, their sensitivity level drops. And we also know that the BMI plays a role in the level of sensitivity in different areas of the body. So it is important to acknowledge that each individual may have a particular sensitivity level as well as a resonant breathing frequency. So in order to build a vibrotactile breathing pacer, we had to study the placement of the device so that we fulfill the inconspicuousness. We had to study how to design a pattern of vibrations, and we had to come up with a personalization procedure for the vibration patterns to individualize that to each user based on their BPM, resonant breathing frequency, and also their level of sensitivity to the vibrotactile patterns. We had a pilot study and evaluated these three with 34 participants using a within subject design experiment. And to evaluate whether placement pattern and personalization procedure have done effectively, we looked at the following variables. So we looked at the breathing regularity to confirm whether the placement position was chosen effectively. We looked at the differentiability between the phases. We made sure that the inhalation and exhalation phases feel different. And this one is a self-reported measure. And we looked at the estimated breath per minute to demonstrate that people were able to pace their breathing with the vibrations, as well as some self-reported measures such as how well they could notice the vibration, they could synchronize their breathing with the vibrations, etc. With regards to placement, which again we consider locations that are inconspicuous, the rationale for the choice of abdomen, chest, and lower back was based on the idea of co-location of haptic feedback on affected part of the body, the need to be inconspicuous to others, the desire to provide a symmetric experience, and the role of biofeedback imagery. We found that the placing the detectors on the abdomen may have led to more regular breathing as compared to the chest and lower back location. Here's our approach. Let's look at the measures we extracted from the breathing data on the right. The important values from these curves are the differences between the heights of the peaks and the valleys and the timing of the peaks and the valleys. Here you can see that the chest and abdomen are moving together. From the y-axis, we calculated the mean and the standard deviation of abdominal movement as well as the mean and the standard deviation of the chest movement. From the x-axis, we calculated the standard deviation of abdominal time and standard deviation of the chest time. We found that the amount of chest and abdominal movement play a mediator role in how much a body placement contributes to the breathing irregularity. That is, a placement on the abdomen contributes to less movement compared to placement on the chest and lower back. So this is what we have here. This is abdomen versus lower back. This is abdomen versus chest, and we can see less amount of movement. In addition, lower breathing irregularity, shown on the x-axis, in terms of standard deviation of chest and abdomen movement, is linked to lower average of mean abdomen movement, shown on the y-axis. So putting it all together, we decided to choose the abdomen to place the pacer of our future studies. This is because it led to less average movement and less irregularity in breathing patterns. In terms of pattern, we created 3 different ways in which the vibration that guides inhalation feels different from the vibration that guides exhalation. In these 3 images, the shape of the first diamond differs from the second diamond. So imagine with one phase you're inhaling and with the second phase you're exhaling. The 3 ways that could be differ were difference only in the frequencies. So imagine the x-axis is sort of representing the frequencies. It's like this one has a lower frequency, this one has a higher frequency. Difference on the amplitude, peak amplitude actually. So these two have different peak amplitudes, and both the frequency, see that this one is more dense, this one is less dense, and the peak amplitude. What we found is that the shape with vibration differing only in the amplitudes, the middle one, led to participants having more difficulty differentiating between the inhalation and exhalation phases. This is regardless of the body placement. Of the remaining 2 options, meaning these 2, the shape with vibrations differing only in the frequency is more preferred because the corresponding personalization procedure, which I will get to later, requires less time to perform. This figure shows the statistics related to this finding. The y-axis shows how hard participants found differentiating. 0 means extremely easy, and 100 means extremely hard. Now, as you can see, most participants did not find it hard to differentiate between the two phases as the means are below the 25. Over here, you can see that the participants did report more difficulty distinguishing between the two phases when the phases differed only in amplitude. So this one is higher than the other two. In terms of personalization, we came up with a 15-minute long personalization procedure to tune 7 parameters involved in creating those 3 different patterns of vibrations. The process involved interaction between the participant and the research assistant shown in the video on the right. I'll be happy to talk about the personalization procedure at the end of the talk, but for the sake of time, I'll focus on whether it was essential to have such a procedure. The table on the bottom shows these 7 parameters that we tuned for each of the 3 body size during the personalization routine for those 34 participants. We found that the variance explained by the model due to individual difference is over here, shown in the purple box, was much greater than the variance due to the body size, shown in the orange box. This is an indication that personalization was indeed a necessary step. So if there's more variance over here, that means people are much more different from each other. And that's why the model had to explain the variance using higher numbers. Now let's see if this actually worked. On the top figure, you see the sine wave-like breathing pattern shown in gray and blue, collected from the chest and abdomen. As you see, they look regular and deep during the time that the pacer was guiding a participant's breathing as compared between trials when participants are answering questions. So here compared to these prices. This is an indication that the participant followed the pacer vibration pattern, in this case, applied on that user's abdomen while the pacer was on. Note no stressor was involved in this pilot study. Also notice that in every trial, the skin conductance, the pink line over here, right, dropped during the 90 seconds of the trial. Skin conductance is an index of psychological calmness. In almost every trial, we had a reduction in skin conductance, which is an indication of calming effect of the pacer breathing. On the left, we see the speed of the skin conductance reduction. It's just a slope. Essentially, that's what we calculated. And of course, if it's below 0, that means there's a reduction. And you can see that the slopes are all negative except for a few. I examined those cases and we found that there's nothing unusual about them. For example, in this case, over here starts to drop, but if you put just an overall line through this 90 seconds, you won't see a drop. On that note, let me show you several prototypes of the pacer, and the last one is equipped with Bluetooth and interact with the app. So what I want you to notice is that the last one plays simultaneous patterns of vibrations on both of these tactors, and the pattern is going to involve 2 different frequencies. So as soon as I put the tactor on my laptop, you should hear the 2 frequency sounds. Notice that they're silent when they're placed on the body, but I just put it on the laptop to make sure that you hear the sound as well. All right. Well, on that note, I'm going to transition to PIV++ paper. PIV++ is a registered study in which we examine the causal effect of the pacer and anxiety reduction in presence of a cognitive stressor. And notice that in the previous paper, we did not have any stressor, but in this study, we examined the causal effect of whether this device actually helped with anxiety reduction. Luckily, we showed that the pacer had a reliable impact on anxiety reduction, and we uncovered insights about who are more likely to benefit from this device in terms of individual differences. We had 100 participants randomly assigned to treatment and control group while balancing for the gender. 3 participants were excluded because of the procedural error. After excluding these, we had 97 participants, 44 in the treatment group and 53 in the control, all balanced across gender. So the treatment and the control group were found to be balanced across a variety of characteristics, including demographics. There was no significant difference between the group in years of education, areas of education, previous training, slow-paced breathing, etc. So based on our PIV paper, we used the abdomen for the placement, and we used this pattern of vibration that is frequency-based. You can see the 2 vibrations. The dual phasicness comes from 2 different frequencies. And of course, we had a personalization procedure. To establish a causal impact of the pacer, we deployed a mixed design experiment. Mixed design experiment is a powerful tool and should be used more often in evaluating efficacy of affect regulation technologies. It enables great statistical power that a between subject design would not be able to provide. And this is because the mixed design experiment addresses the threat to internal validity, which means that you can better rule out alternative explanation for an observed effect. So let's say some participants in a between subject design experiment were really good at affect regulation at cognitive level. And if they all happen to be in a treatment group, then they could drive an observed calming effect that is not even related to the intervention that we're studying. Mixed design experiment setup are not prone to such an effect. Second, it provides insight as to who, in terms of individual differences, would be more likely to benefit from the breathing pacer. For example, individuals low on Big 5 openness are more likely to benefit from the device than those higher in openness. If these individuals were in the treatment group and used the device, they experience a drop in anxiety, but if they were in control group, they didn't experience a change in their anxiety. Now, shifting back to the type of the stressor, we use compound remote associated task, CRA. CRA tasks ask participants to come up with a fourth word that completes a set of three seemingly unrelated words under a time limit. Here is an example: dock, fold, dollar, and the answer is bill. Dock bill, billfold, and dollar bill. Our mixed design experiment had two sets, and each set had 27 questions, CRA question, with each question taking about 9 seconds for a total of approximately 4 minutes per set. Notice that it was easy to use deception in the study by telling participants that we are interested in studying the link between creativity and haptics. To orient ourselves with a CRA task, here's a short demo. Running out of time on a question was equivalent to an incorrect answer. If a question was answered correctly, participants would still have to wait the full 9 seconds before seeing the next questions. This was done to ensure that all participants spent an equal amount of time in the stressor task. Participants were able to see the 9-second timer as well as their cumulative score. A recorded voice provided dynamic accuracy feedback by announcing correct or incorrect. Due to the presence of stressors on the non-dominant hand, participants were required to type with only one hand, which increased the difficulty of the task. Here is a flowchart of the study experimental design. All participants went through the same procedure until end of post-stressor 1. That is over here. At that point, participants who were randomly assigned to the control group went through block 2 while receiving no vibrations, over here, shown with solid line, while participants who were randomly assigned to the treatment group went through block 2 while receiving the vibrations. That is over here, shown with the vibrations. Now let's walk through the study. In the baseline stage, participants watch a 5-minute mindless video of a pipe changing colors. In the meditation stage, participants listen to a 5-minute audio guiding them through slow-paced abdominal breathing techniques. The objective of this stage was to train participants in practicing for breathing with the vibrations that is going to happen later and to estimate the resonant frequency of breathing. The personalization stage estimated an appropriate pace, frequency, and amplitude of vibrations personalized to that participant. Notice that the estimated breath per minute is one of the inputs to this personalization procedure. In the vibrotactile breathing pacer stage, participants practice synchronizing their breathing with the personalized vibration for about 90 seconds. And this shape represents that participants were receiving vibrations during this stage. In the stressor task practice stage, participants were introduced to the compound remote associated task, CRA, and solved 3 CRA questions with no time limit to familiarize themselves. Block 1 contains of the first stressor and 2 waiting periods occurring before and after the stressor. So that is block 1, before and after. Waiting periods called pre-stressor 1 and post-stressor 1 allow time to pass in between stressors so that the anxiety from the stressor would not affect measurements taken at other stages. During the pre-stressor waiting period, participants waited for 2 minutes while seeing the text. You are about to start a set of problems, each with 9 seconds time limit. Your goal should be to solve these problems to the best of your abilities. You will be compared to your peer groups and you will receive information about your performance compared to them at the end of the session. During the post-stressor waiting period, participants waited for 2 minutes while seeing the text, "Wait for the next part to begin" automatically. The stressor task was 4 minutes long and consists of 27 CRA questions with a time frame of 9 seconds each. Let's open it here. All participants followed the same procedure from baseline up until the end of block 1. Right here. The structure of Block 2 was identical to Block 1. In addition to previously mentioned instructions, the treatment group saw the following additional instructions during pre-stressor 2. Please allow your breathing to conform with the sensation of the pacer if you can, whenever you can. Self-reported measure of affect, positive and negative, as well as state trait anxiety sticks were collected at all of these stages. We use SDAI6, which is a brief 6-item version of state trait anxiety inventory with 20 items in order to be able to collect anxiety measures more frequently while minimizing participants' burden. We also collected user technology engagement measure at 2 conditions: warbitactor breathing practice over here, where all participants practice breathing with a pacer and with no stressor, and at post-stressor 2 of treatment group participants over here, who were instructed to breathe with a pacer during block 2. We did this by asking them to rate how difficult it was to notice the pattern, to distinguish the inhalation phase from the exhalation phase, and to pace their breathing with the pacer. All of these ratings were on a scale ranging from 0, meaning very easy, to 100, meaning very hard. In this figure, we discuss our process for ensuring that the 2 sets of CRA tasks had similar level of difficulty across stressor 1 and 2. For each CRA question, Bowden and June Beeman reported the number of the people who correctly answered the questions within 2, 7, 15, and 30 seconds. We assumed that the fraction of people who correctly answered a question within these time frames was indicative of the question difficulty level. To group questions by difficulty, we first performed 2 different clustering algorithms on answering time data and selected the clustering that had the most visually separating and similarly sized clusters. So between k-mean and hierarchical clustering, we can see more visual separation in the k-mean clustering. On the right, you see questions in clusters generated by the k-means visualized in 2-dimensional space with axes corresponding to the first and second principal component. Numbers next to the point represent questions number in Bowden and June Beeman original study. Then we use these clustering results to identify pairs of questions with similar difficulty level. For example, I would say 124 and let's say 127 are at the similar level of difficulty, so one of them will be assigned to block 1 and the other one will be assigned to block 2. Now the question is, did we do a good job with balancing procedure? Did the 2 sets evoke similar level of anxiety and had similar level of difficulty? The figure on the left answers the question on reducing anxiety, and the figure on the right answers the questions about difficulty. The figures on the left shows the NSCR, which is a measure of psychological arousal using a model-based approach introduced in Lida Lab. NSCR refers to numbers of significant, meaning above the threshold, skin conductance responses. You can see that both treatment and control group were pretty much stressed out during stressor 1 and stressor 2 stages. And you can also see that both groups had less psychological arousal during stressor 2. My guess is that this is due to habituation over here. In addition, in terms of difficulty level, we didn't find significant differences in the number of participants correctly answering between the 2 stressor segments. The image on the right, the average of these 2 are relatively very similar. Now the question is, was the pacer effective in reducing anxiety, enhancing positive affect, and reducing negative affect? We pre-registered 3 research questions and we have shown that the pacer reduced anxiety but did not influence the positive and negative affect. Look at the top left figure. We observed an interaction effect between condition, post-stressor 1 to post-stressor 2, and group, treatment and control group, for the state rate anxiety score. And the effect size was 0.33 Cohen's d. The results shows that the treatment group experienced a drop in anxiety from post-stressor 1 to post-stressor 2 compared to the control group. We ensure that from pre-stressor 1 to post-stressor 1, though, there is no interaction effect between condition and group. So the nodes being apart from each other at post-stressor 1 over here is not due to an effect because till end of post-stressor 1, both groups went through the same procedure. We did not observe any interaction effect between condition, post-stressor 1 and post-stressor 2, and group, treatment and control group, for the positive affect, so over here, and for the negative affect, over there. This is the second set of results of the study with regards to the 3 questions on the right side, both in presence and absence of a stressor. The left figure suggests that synchronization with a vibration is more difficult than both noticing and differentiating both in presence and absence of a stressor. We're talking about here and here. The figure on the right suggests that when a stressor is introduced, synchronizing becomes significantly even more difficult. So we see the noticing doesn't change much, differentiation changes a bit, but synchronization becomes much harder. The enhanced difficulty of synchronization with vibration suggests that the personalization procedure should include exposure to a controlled stressor. Doing so could improve a user's ability to synchronize breathing while undergoing a stressor. What makes this pacer as an example of explicit involvement technology is that the user intentionally and effortfully synchronize their breathing with the vibrations. Yet we found that the synchronization is hard when a stressor is involved. Taking these together, these results raise the question of whether implicit involvement technologies, which by definition requires no effort, is better choice than explicit involvement. It is unclear from our results, but we consider a follow-up study to address this question. Now let's shift gears and talk about our exploratory analysis to measure heterogeneous effects. The mixed design of our study provides us with an opportunity to examine what features of individual differences led to benefiting more from using the pacer. Notice that we found a causal effect of the device in lowering anxiety. And that finding could help us to further examine what type of individual differences contributed to this anxiety reduction. For example, if we were able to bin the data into 2 sets, for example, people low on reappraisal versus people high on reappraisal, people low on openness versus people high on openness, and then demonstrate that for one of the bins, we see an interaction effect, meaning if the participants are in the treatment group, they benefit from the device. There's a drop in anxiety, but if they're in the control group, they don't. And in the other bin, there is no effect. Then we can say that people are more likely to benefit from the device if they are low on that feature, for example, openness, reappraisal, etc. And that is what we're going to talk about now. Our approach is for each feature of interest to identify the magnitude of a contribution of the feature to anxiety drop. If the magnitude is large enough, we then look at a cutoff value of that feature, which flips the contribution from drop in anxiety to no drop or even increase in anxiety. For the features with a higher contribution, we concluded further tests to examine whether the predicted drop in anxiety was due to use of the pacer or whether the people with certain characteristics were already predisposed to see the drop regardless of use of the pacer. We did this by training an interpretable machine learning model over a set of features. The model, which is called XGBoost, provides a way to interpret the contribution of each feature to the predictions being made. The contribution is presented by what is called Shapley values. We trained this model only on the treatment group data. As for the labels of the model, we predicted change in anxiety from stressor 1 to stressor 2 only on the treatment group. Over here. We used 26 features to train our model. 11 of the features were related to trait affect regulation and personality measures collected before the study. The remaining 15 related to trait affect regulation and user technology engagement collected at the end of the study and only from the treatment group. Let's walk through some of these features. The emotion regulation questionnaire yields 2 scores representing how much an individual uses the affect regulation strategies of cognitive reappraisal and expressive suppression. The difficulties in emotion regulation scale was kept as a single score, representing the extent to which an individual struggles with affect regulation. State affect regulation measures were collected at post-stressor 2 condition. We asked participants at what extent they deployed each of the following affect regulation strategies of reappraisal: distraction, suppression, and slow-paced breathing to lower the anxiety during the block 2 condition. Here we see the magnitude of the feature contribution on the left and the direction of each feature contribution on the right. So the more spread out on the right, the larger the magnitude. Let's focus on the points on the right first. For each feature, these are the features, 32 Shapley values, each corresponding to an individual in the treatment group data, are distributed horizontally. We mentioned that the treatment group had 44 participants. Here we see 32, and the reason is because these 32 participants were in the training data when we were applying the XGBoost machine learning model. Let's walk through an example. Consider the top row. During study, stressor differentiate. It means how well did the participant differentiate between the inhalation and exhalation phases during post-stressor 2. And as we remember, 0 means very easy and 100 means extremely difficult. Each point represents an individual. The color of the points represent the value of that feature. The bluer points represent participants who could relatively easily differentiate between the two phases of the vibration pattern of the pacer, means values closer to 0, and the redder points represent participants who could not. So these are the people who had harder time differentiate between the vibrations. Now let's look at the x-axis. These are the Shapley values. The more negative the Shapley values, so the ones that are on the left side of this vertical line, the more that feature contributes to a drop in anxiety for that particular participant. The more the positive on the opposite side of the line, the more it contributed to anxiety not dropping or increasing. So this particular participant on the very left, who were able to differentiate between the inhalation and exhalation phases, had a drop in their anxiety. And this feature is a good predictor for the drop in anxiety. Now for this guy over here, they were not able to differentiate between the inhalation and exhalation phases easily. And so this feature did not contribute to the drop of the anxiety of that particular person. For the sake of time, I'm going to focus on these 3 features that we'll be reviewing in the next slide. First is Big 5 openness that had the largest contribution among the Big 5 measures. The second and the third are the 2 affect regulation strategies used during the study. The first one is how much the participant used distraction as a way to regulate their emotion during the stressors portions of the study. And the third one is how much they use the strategy of reappraisal, which means cognitive reframing of a situation to have a different emotional experience during the study. For the openness, the cutoff value of 33, for distraction, the value of 21, and the reappraisal, the value of 71 was computed. How did we compute these? We computed the feature value corresponding to the largest negative Shapley value and the feature value corresponding to the smallest positive Shapley value. We use the average of these 2 features values as the cutoff value for that feature. We binned reappraisal into low and high categories based on the Shapley values. We found an interaction effect indicating that individuals low on reappraisal category had a drop in anxiety over here when they were in the treatment group, but not in the control group. We saw no anxiety change in the higher reappraisal category. However, notice that people who are better at reappraisal, they had a lower anxiety level anyways as compared to people who are not as proficient in reappraisal. So it seems like there is a main effect of reappraisal in the anxiety level as well that is irrelevant to the use of the device. Honestly, these results reduced my anxiety. I was concerned that I would see that people more skilled in reappraisal would be more likely to benefit from using the device. Such people are already good at regulating affect, and their anxiety is lower as compared to those less skilled, as we see over here. Instead, we saw the opposite and more desirable outcome. The device seemed to help those who really needed the help. Notice that you should be skeptical about this finding because A, we did not pre-register this part of the study. This was an exploratory portion of our work. B, the sample size was not large enough for sophisticated machine learning algorithm like XGBoost that we use to extract the Shapley values cutoffs. We only had 44 participants in the treatment group, but these inferences are valuable because they can ignite insights and hypotheses that we can test in future replications of our experiments. For example, we noticed that children diagnosed with autism spectrum disorder are low on openness and usage of reappraisal. And so we hypothesize that these children may benefit from these vibrations to lower their anxiety. Now we're going to test the efficacy of our approach to facilitate affect regulation in this vulnerable population. As for the use of distraction to regulate anxiety, we did not see an interaction effect that is valid. Well, of course, we saw an interaction effect between post-stressor 1 and post-stressor 2 over here, but because we know that this was a mixed design experiment and all participants went through the same procedure till end of post-stressor 1, this result is invalid. So just to summarize, for affect regulation to facilitate reduction of high arousal negative affect in a context appropriate way, I developed an explicit involvement technology. We suggested the early intervention even before affects are generated and the utility of having the user sense the need for interventions. In terms of personalization, it is important to perform the personalization procedure and even better to do it in presence of a controlled stressor. In terms of placement, there is a trade-off in choosing the body side for placement. Placing on the abdomen reduces breathing depth, which is linked to reduction of breathing irregularity. In terms of pattern, frequency-based shapes are more easily distinguishable than amplitude-based shapes. In terms of intervention type, Doppel and emotion check use implicit involvement, which does not involve paying attention or taking any actions with the intervention. In their case, heartbeat like vibrations. We use an explicit involvement, which requires breathing with the pacer. In terms of experimental design, Doppel had 52 participants divided into two groups of treatment and control group. They used a between subject design experiment. Emotion check also use a between subject design experiment. We instead use a mixed design experiment, which is better at addressing threats to internal validity. We had 97 participants divided into two groups, balanced across gender. And the way that we calculated the 100 participants was based on the average effect of Doppel. So we did a power analysis to ensure with a power of 80%, we could see at least an effect size that Doppel observed earlier. Now, in terms of the stressor type, Doppel and emotion check both use anticipation of public speaking task with a deception. We use the CRA task with the deception as well. It's a different type of a deception, more in terms of the link between creativity and haptics. In terms of the dependent variables of anxiety measurements, they both use SDI20 administered twice. We use SDI6 to administer 5 times, and we try to use a smaller version to reduce the burden on the user. Doppel personalized the pattern of vibration to some degree. Emotion check did not. We develop a personalization procedure and we personalize these vibrations for each individual. In terms of heterogeneous effect, which means who benefited from the device, Doppel and emotion check did not investigate who is more likely to benefit from the device. We use exploratory analysis and we suggest that people who are low on openness and low on use of reappraiser are more likely to benefit from our intervention. In terms of the average effect, Doppel had an average effect of 0.28 Cohen's emotion check 0.38 Cohen's and we found an effect size of 0.33 Cohen's. On that note, I would like to stop and thank everyone who helped me with this line of research from many disciplines. These experts have provided an unconditional support and mentorship during my research journey, and I'm so very thankful to each one of them. It takes a city to do a multidisciplinary research, and I'm in debt to each one of you for teaching me something new every day. Thank you very much.